So today we're going to do notes on the exponential model. And so answering, word problems, so application problems on your exponential model. So the way they're going to phrase this in the question, it's like a lot of words that mean something very simple. The rate of change of a quantity, so that's d something dt. I'm going to call it y just for the sake of picking a variable. dy dt, rate of change of a quantity, is proportional to, that means they're just going to have a k value in there. It could be k times something, is proportional to the size of the quantity that you have. So k times y. So dy dt equals k times y. And again, I used y as a variable. You can use, whatever, you can use a letter of the alphabet that makes sense to the problem. Like if you're talking about a population, you can do dp dt equals k times p. The letter of the alphabet is arbitrary though. But this does make sense. The smaller of an amount you have, the slower it's going to be growing, and the more of an amount you have, the faster it's going to be growing. Think about a population. It's going to start out small, and soon it's going to grow kind of slowly, but then once it kind of picks up steam, you have more and more people, the population is going to grow more and more quickly, so it's going to grow exponentially. So that's your rate of change for exponential growth. But this is how they're going to say it in the problem. The rate of change of blah, blah, blah is proportional to, so like you have to read through that and remember, oh, that just means that it's exponential. Right, so the rate of growth of bacteria is proportional to the number of bacteria present. I'm going to use B for bacteria, or you know what, I'll just stick with Y, because the first one I do, let me just stick with Y, because we'll do this in general. You can use B if you want, it really doesn't matter. But the rate of growth of bacteria is proportional to the number present. That means that this is your rate. So dy dt equals k times y. That sentence means this is our rate of change. So it says write an equation to represent this situation. And so we're going to solve the differential equation. So first step is separate the variables. We're going to divide over the y. We'll have 1 over y dy, multiply over the dt, okay, dt, and then antiderivative. And so this side is going to give us ln of y. And this side, remember, k is a constant. That could be 2 or 7 or 5, whatever you have. The antiderivative is with respect to t. So this is going to be k times t. Remember, like derivative of 2t would be 2. Derivative of 9t would be 9. We just did that backwards. And then plus a constant. I realize this feels like I just tried to jam every letter of the alphabet into this problem. ln of y equals kt plus c. It's not even numbers, it's just a whole bunch of letters, right? But we're going to get y by itself. So we're going to exponentiate both sides. And remember, e is a number, c is a number. So we put that out front as one big constant. So it's c e to the power k times t. I dropped the absolute value. I didn't put a plus and minus because these are going to be like real world problems and you can't have a negative amount of something. If you want to be like a purist, I guess you can put the plus minus in there, but for like a real life problem, you can't have a negative amount of something. So these are the two things that you need to remember. This is the rate of change for exponential growth. dy dt equals k times y. And then this is the equation. Y equals CE to the KT. Do you guys remember last year in pre-calc, and this happened before we were out for COVID, do you guys remember doing the problems on interest rates? Do you remember you have, $1,700 that you put in an account and the interest rate is, 2%. How much money do you have in 10 years or whatever? Well, do you remember the one that was PERT? It was your amount equals PE to the power RT. That's this. It's just we're calling it CE to the KT. It's PERT. That's what, and if you want to write PERT instead of KEKT or whatever, that's what this is. Okay, it's exponential growth. So what all of these mean, all these variables mean, y is the amount that you have. So in this case, it's going to be the amount of bacteria, yuck, gross, right? C is the initial amount. And when you were doing those interest rates, the reason we called it P is that's the principal. When you're talking about money, the principal is what you are starting with there. K is the rate of growth. And that's why it's called R over here, R for rate. And then T is time. So that's what everything means. So letter B, there are 300 bacteria present initially. All right, so that means C is 300. So we've got Y equals 300 e to the power kt. So 300 initially. I guess we're like growing them in a petri dish or something. All right, and then there are 700 bacteria 10 minutes later. So 700 is the amount we have. That's going to be Y. So 700 gets plugged in for Y. And it says 10 minutes later, so 10 gets plugged in for time. Write an equation to represent this. Well, what we need to solve for is K, which is the rate. So we're going to solve this equation for K and see what we get. So I'm going to divide over the 300. 700 divided by 300 would be 7/3. And that's going to be equals e to the 10K. And then to cancel out e, we're going to do ln. So you ln both sides. I have to come over here. And then you're going to divide by 10. So here's where the calculator comes in. Where do you get your calculator fired up here, right? We're going to type in ln of 7/3. And then we're going to divide over this 10. So divided by 10. Make sure you close the parenthesis after the 7/3. Otherwise, it'll divide by 10 inside of the ln. All right, so we get 0.084. You can put 0.085 and round up, but I like to truncate. Just take the first three that you see. I think that's easiest, all right? So K is 0.084, and we're going to need to reuse this number in part C. So we're going to copy paste it. So again, to review how you copy these, you're going to hit store, which is right here, STO. So you're going to hit store. That's going to put a little arrow on your screen. And then I would just always store everything as A. You can pick whatever letter of the alphabet if you want, but I just always do A. So alpha A, and then enter. So store alpha A, enter. We've done that before. I'm just reviewing it. Store alpha A, enter. I've got that stored because I'm going to reuse it. Let me set this aside. Now this question asks for an equation. So your equation is Y equals 300. That was your initial amount. E to the power 0.084t. So this is the answer to the question. Write an equation to represent this. So 300 is what we started with. 0.084 is the rate. You need the y and the t in there. Those are the variables in your equation. You plug in time and you get back the amount of bacteria. So letter C says, use that equation to predict the number of bacteria after 20 minutes. All you have to do is plug in 20 for time. And we're going to use our calculator to do that, right? So it is 300. And then e to the power. Now don't type 0.084. You have to do alpha A. You have to copy paste that. And then times 20 for the time. Hit enter. That'll give you your answer. So 1,633 and a third bacteria. We can have a fraction of a bacteria, right? I'm not going to feel sad about chopping them into pieces. All right, let's try that again. So number 2, the rate of change of a certain population is proportional to the population at time t in years. This is a long sentence that just means you're going to use the equation PERT, or y equals c e to the kt. Okay, I'm going to use the calculus variables, but if you want to write PERT, honestly, that's fine, right? So that sentence, that rate of change of a certain population, blah, 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 is proportional to, that means you're going to use this equation. So you just have to be able to read the question and interpret. All right, at time 0 years, this is initially, the population is 500 people. So C is going to be 500. And then after 4 years, so 4 is going to be our time, the population is 750. So that's the amount that we end up with. That's going to be Y. So I'm just going to plug all of those things in. We'll have 750 equals 500 e to the power k times 4. And so in order to write the equation, we have to solve for this rate. So just like we did in number 1, we're going to solve for the rate. So we're going to divide over the 500. So as 750 over 500, that's going to be 3/2 equals e to the power 4k. And then to get rid of the e, we're going to ln both sides. And then we're going to divide by 4. So we're going to grab a calculator. We're going to type in ln of 3/2 divided by 4. And so our rate is 0.101. And we're going to store that because, again, I'm going to need to reuse that. If you just type 0.101, then your final answer is not going to be accurate enough. So store alpha A, enter. So I've got that stored. And so our equation is y equals 500. Again, that was the initial amount of people. So that's the C value, equals e to the power 0.101t. So that is our equation. And it says, at what time was the population 600 people? Now that's the opposite of what we did here with the bacteria. Here we plugged in time. We plugged in 20 minutes time and got the amount. This time we have the amount of people. We want to know what time that, like when in time that happened. So we're going to plug in 600 for y and then solve for time. All right, so dividing over the 500, we're going to have 6/5 equals e to the power 0.101t. And then again, to get rid of e, we're going to ln to cancel that out. And then we're going to divide by this 0.101 to get our time. So this is going to be, when we type this in, it'll be ln of 6/5 divided by, now I want to divide by that 0.101, but we want to copy and paste it. So divided by alpha A. So ln 6/5, close parenthesis, divided by alpha A, gives us 1.798. Again, just take the first 3 decimal points that you see. So 1.798 years. And just make sure to put units for these since they are story problems. So our time was in years. Now, just in case if you didn't have a calculator, like say something like this was non-calculator, right? Let me show you how you would do this if you didn't have a calculator. It's the same exact steps, it just kind of looks a little bit messier. So say you didn't have a calculator and you couldn't get this decimal. You would divide over this 4 and your k value would just be ln 3/2 over 4. Which is what this decimal is. But if you didn't have a calculator, you'd have to just leave it like this. So when you got to this step here at the end, and you were dividing this over, you would have ln of 6/5 divided by, instead of 0.101, you would have this whole thing. And when you divide by a fraction, you multiply by the reciprocal, you would flip this over. So the 4 would go in the numerator. It would be 4 ln of 6/5 over ln of 3/2. So if you didn't have a calculator, your answer would look like this. And if you type this in your calculator, you're going to get 1.798. I'm just showing you that if it was on a non-calculator question, because there's one like that in the homework, your answer looks a whole lot messier, but you're doing literally the exact same. All right, doubling time and half-life. You do these in chemistry. Half-lives come up for, you know, like you have an element that is degrading over time. So doubling time is time. And what you have to remember is these are both times. Time it takes your initial amount to be twice as much. So it's the time it takes it to double. So that would be like putting money into a bank account and you're accruing interest. How long is it going to take to double your investment, kind of thing? But remember, the doubling time is a time. And same with half-life. Half-life is a time it takes the initial amount to be half as much. So again, that's like when you did that in chemistry, you have a certain element and it's degrading over time. How much time is it going to take for you to have half as much as you started with? So doubling time and a half-life. So just remember those are times. So you plug them in for t. Because that's the most common mistake. There's people like, where do I plug in this number? It's a time. So you plug it in for t. Number 3, an element has a half-life of 1,500 years, an initial amount of 200 grams. Find the amount after 10,000 years. I like that our question of the day was about time travel. So it's kind of talking about like time long into the future here. All right, so it's exponential. So y equals c e to the k t. 1,500 is going to be our time. That's the half-life. 200 is going to be c. That's the initial amount. So let's go ahead and plug those in. We're starting with 200 grams. I don't know the rate. We're going to have to solve for that. And then time is 1,500. So I'm going to throw a question at you guys. What is the y amount after 1,500 years? If we started with 200, what do we end up with after 1,500 years? What's going to be like, how much is going to be left if it's a half-life? Okay, let me rephrase that because this wasn't supposed to stump you guys. We started with 200 and it's a half-life after 1,500 years. So what's left? Yeah, there we go. 100. Okay, cool. I don't know. It was so delayed and it wasn't supposed to be a tough one. 100. Let me clarify. You start with 200 and it's a half-life, so you have half as much left, so it would be 100. Whatever you start with, after the half-life amount of time goes by, you have half as much left. So like if you started with 500 grams, then you'd have 250, like it would have half as much. And so when you go to solve this, if it's a half-life, you always end up with a half. 100 divided by 200 is going to be a half equals e to the 1,500k. So honestly, you can almost kind of skip this step and just put a 1/2 there because it's a half. It's a half-life. So you know it's going to be a half. All right, and then we're going to ln both sides to get rid of the e there. And then we're going to divide by 1,500. So we're going to grab the calculator. So we're going to put in ln of 1/2 and then divided by 1,500. I'm pretty sure this comes up in scientific notation. Yeah, because you're dividing by such a big number. I'm not going to bother writing that down. This is that times 10 to the negative 4th because it's such a small number that they move the decimal point over so much. I'm just going to write on my paper ln of 1/2 over 1,500 is our k value. And then I'm just going to store this. So store alpha A, enter, and then I can copy and paste this for the next thing that we're going to do. All right, just because I don't feel like writing the scientific notation. You can, it would be whatever times 10 to the negative 4th. All right, so our equation is y equals, what was our initial amount? 200. And then e to the power of, this, which I have stored as a. And we want to find the amount after 10,000 years. So we're going to times that by 10,000. So I will plug that in and see what we get here. All right, I can't find a place where this all shines. I only have like a few square inches of space to show up. All right, so this is going to be 200 e to the power, our rate, which I've stored. So alpha A times 10,000. And so we have left 1.968 grams. Again, just take the first 3 decimal points, 1.968 grams. Now you want to check and make sure that that makes sense, right? We started with 200 grams. After 1,500 years, you'd have 100 grams, but we went 10,000 years into the future. So it makes sense that you would have a lot less left because we went so much by so many years into the future. So it kind of makes sense that you would not have very much left. All right, number 4. This one's about dollars, cash money here. All right, you put $500 into an account It takes 6 years to double. So this is a doubling time. Your 6 years is a doubling time. So here's our formula. And we're going to put in 500 for the initial amount. 6 years is the time. And we're going to try this again. If it's a doubling time, guys, and we started with $500, how many dollars do we have at the end of those 6 years? There we go. Oh, you guys are with me now. 10 or 1,000, not 10,000, 1,000. Good. So we start with 500. We doubled our money, so we now have 1,000. But honestly, if you want to skip this step, you kind of can, because when you divide this over, you're going to get 2 because it's a doubling time. If it's a half-life, you would have a half there. And if it's a doubling time, you would have a 2 there. So honestly, if you want to skip that step and just put a 2 because it says double, then that's fine. All right, equals e to the 6k. And then ln both sides. And then we're going to divide by 6. All right, so we are going to type in ln of 2 divided by 6. And so again, I'm going to truncate 0.115, and I'm going to store that, store alpha A, enter. So 0.115 is our rate. Oh, and I didn't bring this up back over here, but this rate came out negative. Why does that make sense? Sorry, let me back up a second. I should have asked you guys that question. This rate, I think I forgot because I didn't write it down as the decimal. This rate came out negative. Why did that make sense that this was negative for rates? Yeah, and good, because the amount is getting smaller. Good, I just want to make sure we understood that. So that rate would be negative because you have less and less of the amount. And this one's positive because the amount of money is growing because you're increasing. And hey, do you guys remember that? You pull out that stick-it note. When your amount is increasing, your rate is positive. Decreasing means your rate is negative. I love this sticky note. This sticky note sums up like so much of what we do in calculus. All right, so anyway, we want to find out how much money is in the account after 8 years. So we started with 500. E to the power 0.115, but I'm going to use the stored value times 8, plugging in 8 years. Now your units for this are money, so put your dollar signs there. And we're going to type in 500 e to the power alpha A for the stored value times 8. And there's our money. Now for money, I guess if you want to do 2 decimal points, you can. I'm just always going to put 3 just to be consistent. So $1,259.921. And you can do fractions of a penny. You guys know they do that to you at the gas pumps, right? Like you actually pay whatever it is and then 9/10 of a penny. Did you ever see that little 9 that it's at the end of the money at the gas station? Do you guys know what I'm talking about? You guys ever seen that? They put like a little 9 at the end. Yeah, because what they're actually doing is they're charging you whatever it says and then 9/10 of a penny. So it's actually a little bit, it's like a penny more than what they're saying it is. Anyway, I always do 3 decimal points just to be consistent. All right, and then last one. This one's a little bit different. It's not quite exponential, but I like this problem and it involves a limit. So I like to keep this in here. Sales of televisions in thousands follows this equation. So you pretend you're a TV salesman, you're selling TVs to people door to door, right? 10,000 televisions are sold in 1 year, and the saturation point for the market is 50,000 TVs. Okay, what that means when you saturate the market is you've sold a television to everyone that's going to buy one, and you can no longer sell televisions because everyone who wants one already has one. Televisions are not like things that people buy all the time. Like you can saturate the market with televisions, unlike something like toothpaste, where you have to keep buying it over and over again because you run out and then you have to keep on buying more. It's not like that with a TV, unless you're made out of money. Like unless you're super rich and you buy a new TV every single year. I know there are people that do that, but like how the other half lives there. But anyway, you can saturate the market with TVs and then you can't sell anymore because everyone's got one. So as time goes forward, you're going to saturate the market at 50,000 TVs. So it's a limit. It's limit as time goes forward infinitely. Limit as time goes forward. For this equation, C e to the power k over t, again, that one's slightly different, is 50. And I wrote 50 instead of 50,000 because it says in thousands, right? So as time goes forward infinitely, you're going to level off at 50,000 TVs. You're really not going to be able to sell any more TVs. Buy a new TV after watching. Yeah, every time you watch something, you just buy a new TV. No, it does not work that way. So it's going to level off at 50. So let's work this out. As time goes to infinity, as this t value gets larger and larger and larger and larger and larger, you have k over 100, k over 1,000, k over 1,000,000, k over 1,000,000,000, k over 1,000,000,000,000. That's going to go to 0. You're going to have c e to the 0 equals 50. Remember, if the denominator gets astronomically large, then the fraction goes to 0 because you end up with like 1 trillionth, which is essentially nothing. And then, hey, everybody, what's e to the 0 or anything to the 0 power? What's that going to give us? E to the 0 would be what? And yeah, good. That would be 1. And so C is 50. So we get that C is 50. All right. So plugging some things in here, C is going to be 50. 10,000 TVs are sold after 1 year. So I'm going to put 10 for S, not 10,000, because remember it says in thousands. So I'm going to put in 10 for S, 50 for that C value. And then it's e to the power k over 1, because it said we sold 10,000 TVs in 1 year. So I put in 1 year for the time. And we're going to solve for the rate there. So dividing over the 50, 10 divided by 50 would be 1/5 equals e to the power k. K over 1 would just be k. And then we're going to ln both sides. So ln of 1/5. I'm actually just going to leave it like that. I'll pick up the calculator at the end because that's not super complicated. All right, so it says how many TVs are sold in 3 years. So we're going to have S equals, C is still 50. And then e to the power, k we found was ln of 1/5. And then over time is 3 years. It said how many are sold in 3 years. So this is what I'm going to type in. We'll see how many TVs we sold in 3 years. So I'm going to type in 50 e to the power, let me do a fraction bar here, ln of 1/5 over 3. Now you did not sell 29 TVs. Remember, it's in thousands. And I'm going to round to the nearest whole TV. I will not do a decimal point of a television because that would just be sad. That would mean you broke it into pieces. All right. So it's going to be 29,240 TVs. And that kind of makes sense because the saturation was 50,000. So it's like we didn't quite make it to 50,000 yet. So you still have a few more years to be able to